Chapter 2, Section 6, Solving Inequalities. We're going to talk about, there's quite a bit of language in this section, mostly due to having to deal with different things that can happen with solutions now that we have a possibility of infinity. And usually do with inequalities, you're going to have an infinity of solutions. So they're going to give us some ways to deal with how do we communicate a solution. So we're going to bring in some new methods. Then we're going to get into solving inequalities using the addition principle and multiplication principle, and then using those principles together. That's really stuff we've covered already. There's only one new thing with inequalities with the multiplication principle we'll cover here in a little bit. But first they're going to talk about what are solutions and those kinds of things. Remember, solutions are things that make, for equations, or make the equation true. Well, it's the same idea for inequalities. So if I have like x is greater than 2, and I said, well, if I put 3 in for x, I'd get 3 is greater than 2. Well, that's true, so 3 is a solution. But there's also an infinity of other ones I could use. I could use 2.5, 2 1/4, 5 million. I could keep on going and putting in all kinds of numbers and fractions and so on. So we need a way to communicate that infinity of solutions. But first they tell us here solutions are for this, and they talk about the greater than symbol. This symbol here comes from the number line, and when you have a number line, this is pointing to the right. So this is really a nice way to look at inequality symbols. Is if I said well, I'll wait till I get to some here, but if I said 2 is greater than 1, what it really means is 2 is right of 1 on a number line. I think that's really will fill in the graphing portion and all those kinds of things rather than putting teeth on this symbol and saying it's an alligator and it wants to eat the bigger one. Okay, so and then less than is left of on a number line, and then when they have this line below it, it means that it could possibly be equal. And this is an or statement, which means that if either one of these are true, then it is a solution. So is greater than or equal to. Now this is a logical or, so like if you told one of your children that they can go to the movie if they clean their room or do the dishes, then they could choose one of those, and if they do one of those things, then they'll be able to go to the movie. Or they could do both. They could clean their room and do the dishes. They'd still meet the conditions that you set to go to the movie. Compared to an and statement, which we'll run into later, but ands would be, a logical and means that both have to be true for it to be true. So if I said you can go to the movie if you wash the dishes and clean your room, that means that both of those things would have to be done before you'd allow your child to go to the movie. So there's a difference. And in this case, when we have this combinations of symbols where you have greater than or equal to, that or really means something. And here is less than or equal to. And also an inequality is not equal to. So when we have a slash through things, like the slash through the equal signs means not equal to. Well, then they illustrate, trying to illustrate solutions. So -3 is less than or equal to 5 is what they have here. Well, this is true because -3 is less than 5, or another way to say this, -3 is left of 5 on a number line. Well, that is true. So one of the conditions of the two is true, so the whole thing's true. And in this case, -3 is less than or equal to -3. This is also true because the other condition, the equals part, is true. Now compared to this one, so there's only one way these inequalities can be false, is that both of the conditions have to be not met or not true. So when you say negative 5 is greater than or equal to 4, well, it's false because both negative 5 is not greater than 4, so that's false, and negative 5 is not equal to 4, that's also false. Okay, so both conditions then make that a false inequality. Now they show us inequalities in a lot of forms. Here's negative 7 is greater than x, or you could say negative 7 is right of x on a number line. And if you said that and you put a a mark, and we'll talk about how that mark should be at negative 7, and then you think, hey, all the things I'm supposed to highlight here or show us solutions, the negative 7 needs to be right of it. And if you think about it that way, I think you're going to graph correctly. We get used to seeing things with a variable on the left side, and when it's on the right side, I see a lot of mistakes in graphing and understanding what the solution is. But I can also test. I could go in here and I can make a mark at negative 7 and then check either side. Well, one side of negative 7 is 0. Is negative 7 greater than 0? And the answer is no. So it can't be on that side of negative 7, so it must be on the other side. And so on. Basically, we can guess and check when it's down to these very simple inequalities. Well, we're going to end up with inequalities where you have to do the addition principle, multiplication principles, to get them to a place where I can get a better picture of what the solutions would be. And these solutions are going to talk about here are called a solution set. And they're going to bring in some different ways to illustrate solutions. One of them is a set builder notation and some graphing and stuff. But when I have a solution set, we have solved the inequality, or we've illustrated basically all the values that will make the inequality true. That's what a solution does. So they start out, check, see if this truly is a solution. Determine whether the given number is a solution of y is greater than 6. Well, try 6. It should have said y is greater than or equal to 6, right? Well, I put 6 in there. Does it work? Yeah, it's true. It makes it true because it fits that condition of equal. If I put negative 4 in there, that is not a solution, so that makes it false. Or the other way around, it makes it false, so negative 4 is not a solution. Well, one of the first ways we're going to deal with illustrating solutions to inequalities is by graphing. And we're just talking about a number line type graph. So we just make some rules about what and how we can communicate. So they want us to graph these certain inequalities, like x is less than 2. Or I could say x is left of 2 on a number line. And when I say that, that pretty much tells me where the graph is going to go. Now, because it's not equal to 2, there's no equals part to that, we put a rounded bracket at 2, and then we highlight or shade in the areas of all the solutions and show the direction that it's going. So I could see, hey, I'm going to have a division part here at 2. Even if I get confused by, which way I graph, as long as I remember what this means, I can check some things. I put 2 down here, and then I check one side or the other side. I could check over here and say, let's try 4. Is 4 less than 2? No. So the solutions are not on this side. If I put 0 in for x, is 0 less than 2? Yeah, 0's over on this side. Hey, negative 1 would work, 1 would work, 1/2 would work, and so on. I have an infinity here, so I graph that by shading that. And again, that circular looks like a parentheses at the 2 means it does not include the value of 2, though it gets infinitely close to that. Compared to this one where I have y is greater than or equal to negative 3, notice that they make a mark. This has a square bracket on the negative 3, which means that it includes negative 3. So I could say from this graph, I could say, well, negative 3 should work based on this square bracketing, and does it? Negative 3 is greater than or equal to negative 3? Yeah. And then if you're not sure, test. Try a value like 0 or 10 or something like that, which is over here. And then I find out that I should, highlight this area and show it goes on for infinity to the right. Or another way to say this, the solutions are right of or on -3. Is that what my graph says? Hey, it's on -3 and right of -3. Now we can have an inequality which is a compound inequality. Really what there is an and between these two things. And I could split this into two different inequalities, and that's what they're doing right here. I could really look at this and say this is -2 is less than x, and x needs to be less than or equal to 3. In other words, both conditions have to be met at the same time for this whole thing to be true. So let's just graph this first one. -2 is left of x. Well, I'd have a -2. It's going to be a circular bracket here, this rounded bracket or parentheses at 2, so it doesn't include -2. -2. And then the solutions are going to be, this needs to be left of my highlighted area. So I could check this. I say, well, which side do I go on? It ends up being on the right, but I could check that and say, is -2 less than 0? Yeah, and so on. So I know I'm over here on this side of that. Then I look at the other one, x is less than or equal to 3. Well, I'm going to have a square bracket at 3 because 3 makes that true. And then what side of 3 am I going to be on? Well, it's left of, or I can test values. I could go over here. Does 5 make this true? No. That doesn't make that part true. 5 does make this one true. And I could also go over here and say -6. Does this one make this true? Yeah. But we're only looking for the intersection of these two inequalities. In other words, where the solutions of them overlap or cross, or sometimes called the intersection of those two. And then it basically saying this segment of the number line going from -2 but not including -2 to 3 and including 3 is the solution set, or the graph of the solutions for this complex or dual inequality in a sense. And again, I would go back to the original, and what you think you've graphed, start taking the ones that are easy to work with, like 0 and -1, and so on. Put them in there and see if that works. Now they talk about this alternative notation, this is the one I'm used to seeing, an open circle at 2, representing that it doesn't have the value 2 and then it's highlighted to the left. And this is more like a ray in geometry, and in this case y is greater than or equal to -3 when include the 3, so it's closed circle. That's what I'm used to doing this, but our my math labs and the book and so on is going to use this type of method where they're using that round parenthesis and the square parenthesis instead of the open circle, closed circle. Now they kind of go through this concept part here again, considering basically they want you to see what changes when these symbols change, and doing that stuff, and the differences between the round parenthesis and the square parenthesis and so on. So that kind of covers the way to graphically illustrate solutions. Well, the other one, another one of these is called set builder notation, which is we use these fancy brackets, and the way you'd read this is a set of x such that x is less than 3. And that set notation means I have an infinity of solutions that meet this condition, and so on. And then the other one is this interval notation, which they use kind of what we're doing on the graphs, in a sense that the rounded means that it doesn't include the value right here. Let's go back to some simpler ones, like this one would be x is greater than a, and if that confuses you, put a number in there for a and say x the set of x such that x is greater than 2. Well, this would be a 2 here, and then it would be highlighted this way. Well, this interval notation is like this. I'd have a rounded, or the parentheses here, at 2 if I use 2 for a, and it goes to infinity, but it really kind of, infinity keeps going, so I don't have an end point on it, so they use the rounded parentheses. Here the difference is the equal signs in here, which creates a square bracket, which means it includes a, or if that number was 2 again, that would include 2, and so on. This is a nice little summary of all the different ways. We got the interval notation, the set builder notation, and graphing to illustrate solutions to inequalities. You'll need to use all three in your assignments and on the tests and stuff. Then they go through some examples here of basically graph this, and they want us to illustrate it in all three ways of t is greater than or equal to -2. Well, set notation would be the set of t such that t is greater than or equal to -2. Interval notation would be a square bracket at -2, means it includes it, and it goes to infinity on the right, and the round bracket or round parenthesis, and the graph of that would look like that. So that's inequalities. Now, what do we do when we get more complex inequalities? Well, we can do the addition principle, which says that I can add the same thing to both sides. And they're kind of showing the balance scale and saying, hey, this doesn't really balance, but if I add the same amount of weight to both sides, they still will be unbalanced at the same way. In other words, I can use the addition principle. And they illustrate this with numbers. 3 is less than 7, that's true. If I added 2 to both sides, I get 5 is less than 9. Hey, that's still true. And the same thing happens when we have variables in there. What we're doing is getting an equivalent inequality, or an inequality that has the same solution set as the original inequality. Here's all the different inequalities we could have, and they're showing that this addition of c, or the same number on both sides, is okay to do. So we use this to solve, or basically create, an equivalent equation that is easier to see what the solutions can be. So when I have x plus 2 is greater than 8, I can add a -2 to both sides, and I get x plus 0 is greater than 8 plus -2, or I get x is greater than 6. Now it's easier to guess at what the solutions for this equivalent inequality would be. I could put 7 in there, but I can then start showing the three different ways that I can represent that. I can put it into set builder notation like this: x, the set of x such that x is greater than 6. Interval notation would be it doesn't include 6, so I have a round parenthesis 6 comma, and then it goes to infinity, and then here's the graph of that. Usually what I would do is graph first and get used to this graphical image, because a picture's worth 1,000 words, right? So draw the picture first, and it will probably pull you through, especially this interval notation. You can see the interval notation right here in the graph. Includes, it doesn't include 6, but it goes off to infinity to the right. And now checking can be interesting because, there's an infinity of solutions. You could guess at check and get the ones right and still not have your total solution set correct. So we kind of want to pick and choose. Probably the first one would be, let's pretend it's an equal sign. So if I have, and I get this value 6, well, if I put 6 back into this, I would get 6 plus 2, does that equal 8? And I'd say, well, that's a good sign. That's the division point of which way I'm going to highlight this thing. And in this case, it really doesn't include 6, because 8 is not greater than 8, right? So that's why we got that rounded parentheses. But we still want to go through the process of checking. Now the kind of checking I would do though would be not to use a decimal or a fraction, in this case where I'm looking at a value just to the right of 6. I'd probably take something that's pretty easy to work with, like 10. Now 10 is right of 6 over here. Does 10 plus 2, is that greater than 8? Yeah. That means I'm on the right side of that division. If I want to check the other side, like 0, that's a nice number to add, right? I go 0 plus 2 is 2, right? Is that greater than 8? No. So nothing on this side of this 6 makes this original inequality true. Now we're going to have things where we have the variable on both sides. This is just the same process we go through with solving equations, equal sign ones. So in this case they add a negative, or they add 1 to both sides to get rid of this addition of a negative 1 or minus 1. And I end up with 3x is less than or equal to 2x minus 4. They add a negative 2x to this 2x, which makes it go to 0. And I end up with x is less than or equal to 4. Well, now I can graph that. Now I can put it in set builder notation, and I can also put it in interval notation. But I also should check. I might want to check the other side. Go back to the original, and 0 is very easy to work with. I put 0 in for x and go back to this original. Now I would expect by my graph is that it would not be a solution. It shouldn't make this true, but let's check it anyhow. So if I put 0 in the original here of 3x minus 1 is less than or equal to 2x minus 5. If I put 0 here, I get 0 minus 1, which is negative 1. 0 minus 5 is a negative 5. Is negative 1 less than or equal to negative 5? No. Or in other words, say that is negative 1 left of or on the same place as negative 5. That's not true. So I think I graphed this correctly. And then here's set builder, here's interval. Now the one thing that's different, and they're going to show this, is that when I'm using the multiplication principle, if I multiply or divide by a negative number, it causes a problem. And the first way they're going to illustrate this is with numbers again. If I take this inequality 3 is less than 7, well, I can multiply both sides by 2. Right here is what they're illustrating, and I would get 6 is less than 14. Well, that inequality is still true. But what if I multiply both sides by a negative 2? So here they're showing that, and they go 3 times negative 2 is less than or equal to 7 times negative 2. Or if I do the math, I get negative 6 is less than negative 14. Is negative 6 left of negative 14 on a number line? No, that's not true. What happens when we multiply or divide by a negative? We need to reverse the inequality symbol. And that's what they're trying to illustrate with those examples. So they give us this rule that says if you are using the multiplication principle, which allows me to multiply both sides of an inequality symbol by the same number, if I'm multiplying by a positive number, it's just like the equation part. The less than symbol stays less than symbol here, and so on. Now if I multiply by a negative number, here they're saying C is a negative number, it reverses the inequality. This less than symbol changes to greater than, and so on, and similar with that. This is caution here, multiplying or dividing both sides of an inequality by a negative number. Do not forget to reverse the inequality symbol. There are a lot of mistakes there that happen around that. So these examples are just basically using the multiplication principle to solve these equations. So when I have 1/4 x is less than 7, I want this 1/4 times x to change into 1 times x, the identity of multiplication. How do I do that? I use the reciprocal to change that multiplication into a multiplication of 1. Okay. I should show you this. You're going to probably get this pretty soon.
What is it?
Inequalities.
Inequalities is the greater than less than thing.
Mm-hmm.
How do you know it?
Could you take that spoon and also get me 2 bottles of water? They're in the garage. Yes, you can. Looks like your ankle's doing better, huh?
I can put pressure on it, kinda. It's when it moves in any other way, though.
There's your report card. You haven't been handing in your reading logs, have you?
I have to.
Well, you got a 1 in that.
No. This is all messed up. Always four. Never gotten the 4 on the respectful, responsible, solves problem kind and empathetic thing. I've always just been the average. I never did anything special. Same thing. 3. 4. It's the same class. Okay, whatever. And Hitler, I got a 4 on criterion constraints. Common science is a 4. Niece, homework is a 4. She's given us 3 weeks to turn this thing in the second, 4th week or 3s. And Mr. Big Man had 4s on. Spectral's 4.
Show your mom.
Movement skills are 4. Safety rules are 4.
Yeah, you could be a pretty good athlete if you wanted to be.
Yeah, but I suck at it right now.
Huh?
But I suck at it right now. What's this? Is this personalized or is it just the copy and paste thing?
It's copy and paste, I think.
You want me to show mine? Is that what you want?
She's still up.
Yeah, she is. She's showing no pants. When does this start?
Hmm?
When did this start? I've had 3 tardies since then.
I don't know. I think
This
it's...
just started a while ago. Only classes I've ever been tardy on, though, were Mrs. Estep's in first period. Because that was when I either got a ride from Kennison or I was walking super involuntarily slow.
Give me that, please. So we get x is less than 28. Well, here's the three ways to represent that solution set. Here's the graph of it. We have the rounded parentheses at 28, and it's everything left of that. Or it's a set, builder notation is the set of x such that x is less than 28. Or interval, which is I have a rounded parentheses at negative infinity off over here. It doesn't really include it. I don't have an end point to that infinity. And then I have a rounded parenthesis here at 28. That's why I like graphing first. It kind of shows this interval a little more easier to see it. Well, B here is a negative 2y is less than or equal to 18. Well, they show using division where I would multiply by the reciprocal of negative 2, which is a negative 1/2. Now, when you multiply by a negative, I have to reverse that inequality symbol. So it goes from less than or equal to greater than or equal to. And I would say always, especially when we're dealing with, if you see negatives involved, you definitely want to check your answers against the original to make sure you didn't forget to reverse that inequality symbol. So they end up with y is greater than or equal to negative 9. And here's the three ways you could illustrate that solution set here: a square bracket at negative 9, and then everything to the right of negative 9. And it'd probably be here where I'm doing the graph of this. I would check it against the original. And I'd use a value that's easy to do, like 0. 0, according to this graph, should be a solution to this inequality. So let's put 0 in for y. And I get negative 2 times 0 is 0. Is 0 less than or equal to 18? Yeah, that makes that true. So it looks like I'm on the right side of that. Now, if I would have forgot to switch the inequality symbol, I would think that the solution set was over here. So you'd try like negative 10 and put it in there and see if it works. And I'd get 20 is less than or equal to 18, which is not true. So I do the graph, check your answer. If the graph works or the solution works, then I'd finish it and I'd use set builder notation y, the set of y such that y is greater than or equal to negative 9, or interval, which would be square parenthesis or square bracket negative 9 to infinity round bracket. And then the last part, just like with equations, is, well, we can do both. We can have both addition principle and multiplication principle. And they show us some examples of that, and we can go from there. So in this case, they add a negative 6 to 6, which is 0. 0 minus 5 minus 5y is a negative 5y. Negative 6 over here. I end up with this new equivalent inequality. In other words, the solutions set to this one is the same as this because I followed the rules and did that. Well, the next step involves the multiplication principle. I have to multiply by a negative, so I need to switch that inequality symbol. And I end up with y is less than negative 1/5. Now, if I graph this like this, right, I'd have a negative 1/5 with a round bracket. It would be all the solutions are left of negative 1/5. Is another way to say that less than. Left of, here's that symbol for less than, is that arrow part of the number line. Well, then I'd check that. But I could also check the other side and see something that should not be true. I could still check that if you think about what you're doing. I could put 0 in here. Is 6 minus 0 greater than 7? No, it's not. So it looks like my graph's right because I don't think it should be anything on this side. I still need to check and make sure, that my break point here in my split of my infinity, right, is right. So the other part of that check usually is to go back, treat it like an equal sign is there, put in negative 1/5 right here, and see if I get both sides equal. So I'd have 6 minus 5 times negative 1/5, which would be a negative 1. In other words, 6 minus a negative 1 is 6 plus 1. Hey, that's 7, right? So I get 7 on both sides. If there was an equality in there, that would be true. This example here, they just use decimals. They use strategies again and say, well, one strategy, if you don't want to deal with all these decimals, is multiply both sides by 100 in this case, which would be, I have hundreds here, so I would clear them, and then I end up with these whole numbers. Again, they had a negative involved with this multiplication step, so you have to change your inequality. Here's the graphing, set builder, interval. Now you might want to put into your strategies. Now here's another one where I have to distribute. See, none of this stuff ever goes away. If you were struggling with some of these stuff with equations, you're still going to have these coming up with inequalities where you got to say, well, I got some things I need to do. What do I do? This looks complicated. What should be your first step? It's about strategy, and here we distribute. Actually use the distributive property and distribute. Then we combine like terms if we can to simplify, and you get here, and then I start getting the inequalities. Like terms together, then I try to get the variable on one side of the inequality. Now notice right here, we're used to seeing the x on the left side. You might have been tempted to add a negative 5x to both sides, and so on, and probably wouldn't have been a big deal because this is 0. But you probably would have made a mistake when you were solving because you would have multiplied by a negative and not change the inequality symbol. So a good strategy is if I can keep that number times my variable positive, I can avoid that reversing the inequality symbol by using the multiplication principle, because here I multiplied by a positive. That's just a good note on strategy. So then they go through basically the concepts involved, the multiplication principle. The difference now is that you have to watch out for negatives.